Yeah, I think now we are live on YouTube.
Mates, can you check whether it works well for the YouTube?
Yeah, I think now we are. Yes, are we live on YouTube? I think so. So let me see. So just 4 minutes before the start of the program. We already have the audience in with us. So thank you so much for waiting. We're about to start our program soon.
Wait, I just found this more error. So the time in Beijing is from 9 to 11.
Yeah, uh, really appreciate the efforts from our Chinese colleague. It's a late night in China. Thanks so much for making this effort. Yes, I agree with Dr. Zhu. Yeah, it's quite early for our colleague in the Central Time and possibly Pacific Time. We may also have colleagues join us from other parts of the world. So um, it's really a great pleasure to have all of you with us. I think we'll now it's 8 o'clock Eastern Time, and so I think we should get started. So thanks so much for all of you to join us. I'm Wei Zhang from Michigan State University. Welcome to the second webinar jointly sponsored by the Soil Science Society of America and Soil Science Society of China and on soil health. And so I'm the person who is responsible on the technical side. So I'm going to uh, talk with you briefly about the format of this webinar. So for all the audience, and you're welcome to type your questions on the Q&A section. So after each presentation, we'll have time for question and answer, but we may not have time to address all your questions, but we'll do our best. And the program will start with a opening section with remarks given by the president of Soil Science Society of China and a president-elect of Soil Science Society of America, followed by the presentations with 4 distinguished speakers and the summary discussion by Dr. Yongguan Zhu. So I won't give introduction to all the speakers and the moderators at this point, and they will appear in the program as scheduled. So with that, I'm gonna turn the microphone to Dr. Yan Xiaoyuan. He's gonna moderate in the opening session.
Hello, everyone, and good morning or good evening. And now, firstly, let's welcome Professor Jiabo Zhang, the president of Soil Science Society of China, to give us a welcome speech. Professor Zhang, please.
Oh, okay. Dear Professor Michael Thompson, President-elect of the Soil Science Society of America, soil scientists from China and American and other countries, ladies and gentlemen, good morning and good evening. As we gathered here today, we recognize fundamental importance of soil sustaining life on our planet. The health of our soil directly impact food production, water quality, climate regulation, and overall ecosystem resilience. Therefore, it is imperative that our engaging, meaningful discussion and knowledge sharing to advance our understanding of soil health and its implication for sustainable agriculture, environment, conservation, and human well-being. Soil health is a multifaceted concept that encompasses the health, the physical, chemical, and biology properties of soil, as well as its capacity for functioning as a living ecosystem. Health soil support diverse micro-communities, promoting nutrient cycling, enhance water retention, and provide stable foundation for plant growth. Furthermore, they play a crucial role in mitigating climate change by sequestering carbon and regulating greenhouse gas emission. By acknowledging that in significance of soil health, we acknowledge interconnectedness of all life forms and environment. The collaboration between the Soil Science Society of America and Soil Science Society of China exemplify the split international cooperation in addressing global environmental concerns. By coming together this webinar, we have the opportunity to exchange insights, share best practices, foster cross-cultural learning. Our correlative expertise and environment can control development of our holistic approach to soil health management and transit the geographic boundary. In conclusion, we extended my gratitude to all participants for your dedication for soil health. Thank you very much.
Thank you, Professor Zhang. Now, let's welcome Michael Thompson, President-elect of the Soil Science Society of America. Michael, please.
Hello. Well, I'd like to echo President Zhang's welcome to everyone. On behalf of the Soil Science Society of America, I'm delighted to be here and welcoming everyone to this webinar co-sponsored by these two very important scientific societies. This event, as you know, is the second webinar that we have organized, and the topic, of course, is one that is of interest to scientists and the public worldwide. Like President Zhang, I would like to sincerely thank the entire organizing team from both societies, the team that has put this webinar together. Thank you to each of the participating speakers and to all those behind the scenes who are helping to make this a successful meeting. All of your efforts are greatly appreciated. You know, our two scientific societies have so many things in common. We represent countries that have diverse soils. Our soils provide diverse services to human societies and to the earth. And we represent strong scientific and academic institutions that conduct research and educate students about soil science. I think we're all charged with the task of wise stewardship of Earth's soils. Human health, food security, mitigation of climate change, they all depend on environmental quality, on soil security, and our topic today, of course, soil health. So the webinar today is one small step that we can take to share our knowledge, to connect scientists and teachers and students with one another, and to preserve and improve our channels of communication. We're so glad that all of you have joined with us on this journey. So welcome to this webinar about soil health.
Okay, thank you, Michael. Now, Professor Zhang, it's time for a group photo, right? Wait, Zhang, your microphone is
Yes.
shut
Yeah.
Yes. Thank you. Thank you for the reminder. All the panelists, could you turn on your camera? And so Fang, could you also take a screenshot? I want to make sure that we got this screenshot. And all right. All right, I think I'm successful on my end. So maybe one more. All right. Okay. So I think we're doing really well on time, actually 2 minutes early, which is a very good sign. So I think we should turn this over to our first moderator of the presentation section, Dr. Elizabeth Ricky from Soil Health Institute in the United States.
Thank you. Good morning, good evening. Our first presenter today will be Limi Zhang from the Research Center for Eco-Environmental Services with the Chinese Academy of Sciences. And her presentation today will be titled, Soil Health Depends on Inherent Soil Properties in the Black Soil Region in Northeast China. Dr. Zhang, would you like to take it away?
Okay. Oh, yeah. Sorry. Can you hear me and see my screen now?
Yes.
Okay. Yeah. Yeah. Thank you very much. Sorry, I need some time to fix. Okay. Yeah. Yeah. Thank you. Wade and Fan and all organizer and the leader for giving me this very great chance to communicate with you here. Yeah. Today I'm going to show some our preliminary result on soil health assessment for the black soil region in China. For the soil health assessment, I'm just a new student here. You have a lot of experts, so Also, hopefully you can give me more suggestion and help. Maybe a little bit background about black soil. Black soil are characterized by a thick, dark color soil horizon rich in organic matter. There are mainly four area black soil distributed. One, the Great Plain of Russia and Ukraine. Another one is the Great Plain of U.S., Canada, and Mexico. The third one is located in northeast China. And the fourth one is in the Pampas and Chaco region in South America. Even though they are only the black soil only cover 7% of land surface in the world, but these four areas are the very important crop production area. In China, like the black soil in northeastern China, are mainly located in the northeast part, in like Heilongjiang province, Jilin, Liaoning province, and some area in Inner Mongolia. This area accounted for 1/4 of cultivated land in China and produced almost 1/4 country's total grain output in China. So they have a very important role in food supply in China. And the black soil in China was reclaimed since 1950 and 60, even to 1970. Following the intensive land use, the black soil in China is experiencing very serious soil degradation, particularly like the very fertile topsoil layer is thinning, almost by reduced by 20 centimeter. Basically because the very heavy hydro and wind erosion. These two pictures show very common phenomena in the northeast part of China in summer and in spring. Like in spring, my colleague packaged her like this to against very heavy wind. So the soil organic carbon decreases very quickly, almost by 20% since reclamation, and also soil acidification and compacting is serious in this area. So in recent years, the government made great effort to protect black soil. For example, in 2022, the first land law for black soil was issued for black soil area, and also a lot of action are taken to stimulate the application of conservation tillage, like rotation and straw return, and also zero tillage, something like this. Also, there are quite a lot of big projects are launched by Chinese Ministry of Science and Technology, and also by CS to try to encourage science and technology innovation for black soil conservation. In 2021, CS launched a strategic priority research program we called Black Soil Granary, which are mainly leading and designed by Professor Zhang and Professor Zhu. So I participated in some of them. The basic question we try to address is how's the soil health status in the black soil region in China, and what's the main driving force for the special pattern of soil health. To answer this question, firstly, we need to know how to assess the soil health in this area, in this region. So as for soil health, we know like the conception of soil health has been extended from soil fertility quality to multiple ecosystem function, including in addition to crop production, soil's other function like water conservation, human health, climate change response, and also biodiversity maintenance, and so on. So the previous method for soil quality assessment are challenged greatly, and this previous method mainly focused on soil fertility or environmental quality, but consider less on the ecological system function. And also the previous methods are mainly based on chemical and physical indicators, less use biological indicator. So in this project, we firstly need to establish a method to assess soil health in the black soil area. We started this work since 3 years ago. Yeah, at the beginning, we carried a large-scale field survey and sampling. For the last 2 years, we got almost 1,000 soil sample, including 700 upland and more than about 200 petty soil sample. And this area, we collected another 500 sample from this 3 area. But we have not got the data at the moment. So today I only show the data from the last 2 years from this red point. Yeah. After we get this soil sample, we did a lot of measurement in the laboratory for soil physical, chemical property, and also did a lot of microbial diversity analysis and also microbial activity, including microbial biomass, carbon, nitrogen, and soil respiratory quotient, enzyme, and some nitrogen transformation process rate, something like this. And there are so many parameters. So first, at the beginning, we just measured as more as possible parameter for just 150 sample, including paddy soil and upland soil. But after we get a preliminary data analysis, we found like the data in paddy soil and upland soil are totally different. So we decided to divide them separately. So here I just showed the data from upland soil. So from the first small data set, we selected 24 parameters for next step. For next step, we enlarged the sample size to 345, and then measured the 24 parameters. From these 24 parameters, we further focused on the 13 parameters as the minimum data set for upland soil assessment. Yeah, we did this data screening based on mainly on PCA analysis and correlation analysis, and in combining with our opinion or experience like this. So these are the data processing detail. From the 24 parameters of 345 sample, we focused on 13 parameters, including pH, EC, and this 13 one. And then we further classified this indicator into different function group, mainly based on the recommendation from USDA and also Cornell assessment framework and some other literature. For example, for bark density and EC value, we use the function group less is better. After classification, we calculated the score of each function, use different model. These are the score pattern for each 13 parameters. After that, we calculated the soil health index based on weighted average method. This is the score distribution pattern among the soil sample, among region and the soil types. And generally, like most soil sample, 70% sample got the median score value. Only 6% sample got quite high value. When compared with the USA dataset, we found our score value are generally lower than US soil as for the median value and maximum value. And when we try to put all this score for each set into map, we can say there's a large variation of the score among different areas. Particularly, there is a trend, like an increasing trend from the southwest to the north part. And the random forest analysis suggested that climate factor, like mean annual temperature and mean annual precipitation, have significant influence on soil health. And the soil property, like organic carbon and total nitrogen, explained the highest contribution on the soil health score. Also, there is a clear linear decline trend. Soil health decline with the increased temperature, and distinctly ordered by soil type. Like the soil type, the 6 soil type in blue color are generally considered as the good soil type with high fertility and healthy degree. And this soil type can be clearly classified into 3 groups with high and medium low score. And the soil health index score is positively related with organic carbon, total nitrogen, water holding capacity, and microbial carbon, biomass carbon, and even latitude, but negatively with bulk density. But it's a pity we cannot find any significant relationship between soil health index and the microbial diversity, even alpha diversity and beta diversity. And we are very curious, like what's the difference between healthy soil and unhealthy soil. So we tried a different way to test them. And finally, we found like all soil can be clearly clustered into 2 groups. In light of soil respiration, microbial biomass carbon, and also respiratory quotient. One is the high one, another one is the low one. When we compare these 2 parameters, to soil respiration and the quotient, also it can be clearly grouped into 4 groups, with corresponding with different like soil health score. For example, the high respiration and the low quotient soil generally have higher soil health score, but the soil with low respiration and high quotient generally have very lowest soil score. I think it's really interesting, as like the high respiration means microbial have a high activity, but for high quotient means microbial may have very low energy use efficiency and under stress. So these 2 parameters can really indicate the soil health. We think it's quite important. And we also constructed the structure equation model to identify, to quantify the effect of climate and soil pathogenesis factor. It showed these two factors can have significant influence on soil health. Mainly will influence soil physical, chemical, and biological property, even though they have significant influence on microbial alpha and beta diversity. But these 2 diversity have very weak correlation with soil health. So as our soil sampling area spanned a very large scale, even from north to south, we cannot establish a relationship between soil health score and the crop yield. So we did some planting experiment in greenhouse, try to test if our health score assessment is reasonable. So we generally plant the ryegrass in different soil, but put them grow in under the same condition. Yeah, from this picture we can see like the soil looks like quite different color, different texture, something like this. Finally, we found like the soil with high soil health index generally produce high above ground eelgrass biomass, and the soil type with high soil health score generally have high regress biomass than those soil with low score. Yeah, this picture show very clearly like the below ground root growth condition. For this soil from the south part in south part North China, with quite low soil health score, and the root is not good, and the biomass is the lowest in. But for this soil with the high score from the north part, generally got a high ryegrass biomass. So this means, yeah, and the soil assessment score is, I think, is reasonable, can reflect the soil's potential ability to sustain the plant growth, something like this. So generally, all this data suggests like the climate and the soil type or pedogenesis process play quite important role in determining the current soil health status. And also our study suggests that soil respiration and quotient are quite important property to differentiate the difference of soil health status. Yeah, that's basically conclusion or preliminary conclusion we got at the moment. Yeah, our second purpose is try to identify some microbiome indicator for soil health, but it's pitiful. We did amplicon sequencing for more than 500 samples and try to identify to see if the soil health grade is associated with microbial diversity, but microbial diversity only significantly different among different pH grade, not soil health score grade. For the beta diversity also, soil pH and the soil type and other factors are the main driving force, not closely associated with soil health. We also tried machine learning method to try to identify some indicator for soil health. We tried two methods, including classification method and regression method, to identify, to firstly to select the top 50 OTU for each NG value parameter, and then figure out the overlap OTU with event analysis. Yeah, when we use the soil health score or grade, we can identify quite a lot of OTU associated with them, but this OTU generally also distributed in different soil score grade sample. So it's really hard to recognize some indicator are really can reflect the soil health grade. But for soil pH, it's quite easy to identify some taxi some bacteria or fungi group which sensitively respond to soil pH, like bacteria, a lot of OTO in this phylum are positively related with soil pH, something like this. We also tried all 13 parameters to try to identify them, but only pH, SOC, and TN are very reasonable. And for SOC and total nitrogen, also it can be grouped three group corresponding to the lowest medium and the high SOC or total nitrogen grade. And we think like these two parameters explain the highest variation for soil health. So we think maybe this is a good clue to focus next step. For example, like we can identify some OTO or some bacteria or fungi group that very sensitively respond to SOC change. Particularly some OTO, most OTO in bacteria phylum are positively related with SOC content. Some OTO within fumicate or acid bacteria are negatively, something like this. For total nitrogen, it's similar. The identified biomarker are quite similar as the SOC biomarker. So we think maybe it's deserved to focus on this text or this bioindicator. Yeah, we also tried a lot of metagenomic analysis. We did metagenomic analysis for 160 samples. All this data based on KO functional gene database. All this functional gene are also mainly shaped by soil pH and very close to each like carbon or nitrogen process, but mainly clustered by soil pH, not very not closely associated with soil has grade, something like this. Anyway, just like the microbiome indicator is a big headache for us, and it's still pending, and also we have a very long way to go for establish a complete soil health assessment. Yeah, that's all my talks. Thank you very much, and hopefully and any comment and suggestion are welcome. Thank you very much. So
great, thank you so much. It was a great presentation. We have a couple of questions in the chat that I think we can get through maybe quickly before the next presentation. The first question is about how did you go about measuring the respiratory quotient that you showed the data for?
Okay. Oh yeah, just like use the we measure the soil respiration, and then we have biomass carbon. Just divide them. Yeah, we can get just the quotient means unit biomass, the respiration of unit biomass, something like this.
Fantastic. One more quick question. Can you go through maybe in a little bit more detail how the soil health index scores were calculated?
Just based on like weighted average, we just like summarize them and then yeah calculated the mean value. Like for each parameter, we have to go from 0 to 100, and then we just summarize them and then divide the 13 like this. Mainly following the method of Cornell assessment method. Yeah.
Great. All right. Well, to try and keep on track on time here, we're going to go ahead and move on to our next presentation. Thank you again. You can look for more questions in the chat if you can stick around, maybe one of those. All right.
Yeah.
Well, thank you. And
thank you, Lynn. Thank you, Will.
our next presentation is by Dr. Harold Van Ness from Cornell University, and the title of his presentation is Factors of Soil Health and Benchmarking Approaches.
Great. Thank you very much, Liz. Happy World Soil Day, everyone. And thank you for either getting up early or staying late. I'm going to build on Dr. Zhang's presentation. And hold on, let me get rid of my screen. I'm going to build on that. And it was actually a great introduction to what I'll be talking about, which is going sort of beyond the inherent factors, but looking at cropping systems and management. So co-authors are Joseph Amsili, Valentina Rubio, and Debbie Aller, who are members of my team here at Cornell University. So let's start with the slide advancing. There we go. So as perhaps some of you know, and Dr. Zhang already kind of referred to it, over 20 years ago, we decided it was important to have sort of practical measures of soil health. So we launched what became the Comprehensive Assessment of Soil Health approach, or conveniently abbreviated as CASH. And we built a soil health laboratory here at the university. And it's based on physical, biological, and chemical indicators. The physical available water capacity, 2 levels in the soil of hardness, aggregate stability, then 4 biological indicators, including organic matter, soil organic carbon, and total carbon, protein, soil respiration, permanganate oxidizable carbon, also referred to as active carbon, and then basically a standard soil nutrient and pH analysis. So one of the advantages of having started that early and receiving a lot of samples from all over the U.S., but also other places in the world, is that we've now built up a very large soil health database that we can use to gain further insights. So just to kind of reiterate that this soil health test is based on indicators that represent important soil processes, so physical, biological, and chemical processes that are listed here. So we believe that we're sort of capturing all of the important processes that are relevant to the functioning of the soil, and thereby the ecosystem services that are being provided. And I won't go into detail on that. And similarly to what Dr. Zhang was saying, maybe I'll go back to the previous slide, that we do also look at an overall soil health score, which is the unweighted mean of the values that are interpreted in these soil health scores that were mentioned earlier. So out of this research, one of the main ideas that I think came out of that is that we can sort of recognize 3 different factors related to soil health. So one is sort of the natural differences in soils that Dr. Zhang elaborated on. And that's basically related to things like climate, parent material, biological processes, et cetera, that we know from our introductory soil science courses. And that's, of course, we don't have any control over that. That is basically the soil as it was naturally. Then second, we have land use. It could be, say, urban versus agricultural, but also within, say, agricultural, is it a cash grain system where maybe corn, soybeans, or wheat are being grown? Or is it an animal-based system, maybe dairy? Is it perhaps perennial fruits or pastures or something like that? And there's limited control. Typically, that type of land use is locked in more or less. A cash grain farmer is not all of a sudden going to become an apple grower. So there's limited control there. And then third, we have management, and that more relates to the type of tillage systems, or whether organic amendments are introduced, or cover cropping and things like that. And that's where a farmer has the most control. So let's look at these different factors. So the inherent soil properties, and I think most of us are more familiar with that. And we have an indicator like available water capacity, and it relates very strongly to soil texture. And this is, this could have come out of an introductory soil science book. And so this is something we know, but it's relevant in terms of soil health in that when we measure this property, available water capacity, as part of soil health assessment, we need to make sure that we interpret the numbers correctly and that we account for the fact that different soil textures are associated with different expected values for available water capacity. And as it turns out, that also is the case for other indicators. So here are several soil biological indicators. And let's see a focus on soil organic matter. If we have the four groupings of texture classes, basically, we see that, of course, coarse textured soil tend to have less organic matter and less carbon than, say, fine textured soil. We know that, but it's relevant in terms of interpretations. But we didn't really know that was also the case for, say, permanganate oxidizable carbon or respiration. A little less the case for protein, and it has more to do with extraction efficiency. But again, we need to interpret those values in the context of soil texture. And so that brings me to the more national interpretation scheme that's referred to as the Soil Health Assessment Protocol for Evaluation, that accounts for texture, classification, suborder, and climate factors. And I'm not going to go into details on that because Kristen Vuum will be doing that in about an hour, but I just wanted to introduce this idea that we've been able to, through this collaborative effort with Kristen's group and statisticians at the University of Missouri, we've been able to kind of capture these inherent properties. So Kristen, we're looking forward to your presentation on that. So I'm going to now go into depth to look at the land use and cropping systems aspects and how that is impacted, and also how biomass cycling appears to be really important. So just to give you a little bit of a cartoonish introduction to that, if we think about a natural system that tends to be a soil building environment, we know that there's a lot of biomass production, grasses or trees or whatever. There may be animals, and there's most of the carbon and nutrients are cycled back into the soil, either directly through plant biomass or maybe through an animal, and then the urine and feces that end up in the soil. So in this case, we have a very happy worm because there's plenty of energy and nutrients in the soil. Now, as we went to more intensive agriculture, especially specialized agriculture involving cash crops, we have a very different situation in that a lot of times most of the biomass is being harvested and removed from the field. An extreme case might be something like cabbage production, where almost the entire crop is being harvested and there's virtually no carbon and nutrients going back. If we're thinking about corn or soybeans, the harvest index may be something like 45%. So a lot of the carbon is being removed, but especially a lot of the nutrients are being removed. Say phosphorus may be removed at the 80% rate. So there's a lot less cycling also if you account for erosion and carbon losses from tillage. And so there's much less turnover of carbon and nutrients. And so we now have a nervous worm because the soil is deficient in these nutrients and carbon. Now, a lot of times we replace the nutrients with synthetic fertilizers. So that solves that problem, at least on the short term. But the carbon is typically not being replenished. And so that's why we often see this soil health degradation. Now, I wanted to show this map. If you have never seen this, I think it's very profound. And it kind of links to our two continents because when you think about carbon and nutrients and the water that is required to grow these crops, we're shipping massive amounts of these crops across the globe, mostly from the Americas. This is for soybeans, which is sort of the ultimate global crop. from the Americas, the US, Brazil, Argentina, Uruguay, and it goes to East Asia. And so that creates some challenges in the Americas because we're shipping a lot of carbon and nutrients away off our continent, and it can create problems in Asia because now you have this accumulation of nutrients and carbon also creating problems. And you can see the numbers here on this graph. And by the way, this is from Rabobank. If you've never seen these types of data, this is really a profound part of what impacts soil health around the globe. So an interesting example here is because of this high global demand in these cash grain crops, especially soybeans, we've seen in some areas of the world this transformation of agriculture. In the US, it's been for a long time. In Brazil, as you know, maybe about 30, 40 years ago, we've seen massive areas being put into grain crop production, and also the Pampas area, natural grasslands in South America, in Argentina, Uruguay, have many acres and hectares have been converted to soybean production. Now, soybean, we're finding is a particularly challenging crop because it's a very low biomass crop. So you look at this picture, soybean doesn't have a lot of biomass. When you harvest about 45% of that biomass as grain and maybe 80% of the nutrients, and you take that off the field and you ship it across the world, that is not good for soil health. And we see this tremendous soil health degradation. And we know that there's this relationship between the biomass inputs and the overall soil health. So the less biomass goes back into the soil, the more soil health is going to be challenged. So we, for the New York situation, and this is a map of the state of New York, the city is right here in the southeastern corner. We had a very strong database, so we decided to look into the different cropping systems because they cycle different levels of biomass. So, for example, we know that a processing vegetable system recycles very little biomass. Most of the crop is being removed and sold. Annual grains, we're talking about maybe corn, soybean, wheat. Typically about 45 to 50% of the biomass is removed. In dairy crops, that can be corn silage or alfalfa. It varies a lot in terms of how much biomass is removed, but obviously corn silage leaves very little biomass. Pastures, of course, have a lot of cycling of carbon and nutrients through the animals. Then we have also orchards, and we have mixed vegetables, which is typically highly intensive vegetable production, many of them being organic. So how does that really relate to some of these soil health indicators? Well, here you see that organic matter is fairly significantly impacted by the type of cropping system, with pastures, of course, having the best outcomes, and processing vegetables and annual grains the lowest. And we can relate that to the amount of biomass that normally is being cycled in these systems. You can see that these mixed vegetable systems, very intensive, often involving, say, compost or manure applications, are doing better, and dairy crops and orchards are sort of intermediate. When we look at aggregate stability as a physical indicator, we see that pastures stand out even more because there's no disturbance, there's no tillage, and there's a lot of biomass. That means carbon and nutrient cycling. And we see in this case, processing vegetables typically involving a lot of intensive tillage and very little biomass cycling have the worst outcome. So cropping systems are important and need to be considered when we interpret soil health data. So in New York, we were very fortunate that about 2 years ago, some legislation was passed, the Soil Health and Climate Resiliency Act. And as part of that legislation, we were asked to establish appropriate voluntary standards and objectives for soil health. So that got us really into doing work related to soil health benchmarking. So we refer to these as the production environment soil health benchmarks. So production environment relates to sort of the inherent soil properties, the climate, but also the cropping system, whether say annual grains versus maybe a dairy system or a vegetable system. So we're using the same approach of scoring functions that Kristen will go into details about, where we look at the distribution of soil health outcomes, and then we define benchmarks as maybe the 75th percentile or the 90th percentile. So we kind of look at the 75th percentile as there being a resource concern, and the 90th percentile is maybe an aspirational goal. So the 90th percentile in this distribution means that 10% of the farmers have been able to achieve that level of soil health. So that is a reasonable aspirational goal. And so this is the case for organic matter. So just to give you an example, if a field comes out with an organic matter level that you see here, maybe about 2.5%, then what you'd like to do is you'd like to see them move that up at least to the 75th percentile, but ideally to the 90th percentile. So this way you have realistic benchmarks that are sort of based on statistical distributions for soil health. And we believe that's a more realistic way to go. So here are just some numbers that show these benchmarks. This is for the 90th percentile for coarse textured soils, because it still has to be done in the context of soil texture. And we see these benchmark values, okay? So we're actually in the process of rolling this out and getting some public review of that. We're also proposing that pastures are sort of the aspirational soil health benchmark. That is that, you know, pasture sort of represents the more or less ideal situation for soil health. One could also select a natural soil health criterion. That's another way to look at it. But for that, we don't have enough data for that, so we're selecting pastures to do that. We're also communicating to farmers what their soil health status is, and we do the same type of peer environment referencing, where for a hypothetical farm here, it's actually a real farm, but we just changed the name, where a field is indicated, and then we also indicate where, in general, fields that are in a dairy system, what kind of a range and mean values they have. So that way farmers can benchmark their fields relative to that of their peers. And hopefully that will stimulate them to improve their soil health. So finally, I want to talk briefly about the mapping of soil health. So, you know, the typical soil maps are focusing on sort of these inherent characteristics of the soil, and that are, you know, typically not very dynamic, you know, especially texture, organic matter content, especially. So with the knowledge that we gained from our analysis, we wanted to see whether we can use publicly available data to map soil health and to get a better idea of the distribution of soil health. So we used machine learning technology to do that. This is part of Valentina Rubio's PhD research, by the way. And here's a map of the state of New York that has the main different land resource areas. And you can see the samples. We had a pretty good distribution. And so we used the machine learning to predict these soil health indicators. And I'm going to focus actually more on the composite soil health index in the interest of time. So that's sort of the overall soil health. And we used information on inherent properties, so climate and soil and topography, like slope, order, drainage class, pH, clay, silt, bulk density, and organic matter. And they're all available from public sources. And then we also had some additional land use related covariates, mostly cropping system. For example, you know, whether it was annual crops or pastures, mixed vegetables, hay, the frequency of those crops, and for example, how much pasture or how much vegetable was in the system. And then we looked at the biomass or the productivity using satellite information, using mainly NDVI or plant biomass data. So what came out of that? So on the left here, you have the graph that shows the importance of the different prediction variables. And like Dr. Zhang said in the previous presentation, climate was really important. We also see that texture was important, and we see that certain land use practices were also very relevant, notably, the cropping system and how much hay was in the system. So you see here these importance plots, these so-called SHAP plots, that if you have more pasture in the system, you have better soil health outcomes. If you have more annual crops in the system, you have less favorable soil health outcomes, and the same with vegetables. Overall, higher NDVI, more biomass results in higher soil health outcomes. And then we can, once we have these models developed, we can actually map soil health, and you can see that in this map here. One of the interesting things about this map, if you're familiar with agriculture in New York State, is that the areas that have the less favorable soil health outcomes are the more intensive agricultural production areas. These were actually the areas in the state that naturally had the best soils for agriculture. But now we find that from a soil health perspective, they have degraded the most. So in a way, we have almost a reversal of the quality of the soil. All right, so with that, just some conclusions. Soil health is influenced by those three major factors: the inherent properties, the land use type and cropping system, and then management practices within. Biomass is an important driver of soil health, and more biomass production you have. So, for example, soybean being a low biomass crop, and the more cycling you do, you see favorable soil health outcomes. We believe that soil health interpretation and benchmark needs to be based on peer production environments so that they're relevant. And we've shown that you can do mapping of soil health or dynamic soil properties using machine learning methods and accounting for the relevant publicly available input data. Okay, with that, Liz, I'm turning it back to you.
Great. Thank you, Harold. Are there any quick questions out there floating around? I don't see any in the chat right now. Well, if not, I have a quick question for you, Harold. So really interesting setting the aspirational goals, having those kind of different levels. Do you plan to update those curves over time? So like say, for instance, you have a peer group where the majority of folks have adopted, say, cover cropping or no tillage. Would that change where you set your aspirational goal, say 10, 15, 20 years from now?
Yeah, that's a good question, and we may need to do that. So one of the advantages of basing it on a peer environment or the distribution within a context of a cropping system is that it's very realistic, right? But you're bringing up a point. Once everybody, if we do see everyone go up, which of course we would be very happy to be able to conclude after 20 years, then yeah, we may need to make some changes. We will probably need to make some updates anyway as our database becomes stronger. Yes.
Perfect. All right.
Yeah.
Go for it.
Yeah, very excellent work. Yeah, I'm very wondering. Sorry, maybe I missed some information. Like, how do you consider the impact of temperature, rainfall, and also how to calculate the impact of management and land use, something this factor for.
So yeah, that's a good question. So in our benchmarking, so the climate impacts are implicit, and Kristen will address that in her presentation. But the management is not part of the benchmarking because that's what you would like to see change. That's the one where we would like to see farmers move their management towards more favorable soil health outcomes. For example, by changing tillage systems or bringing in cover crops or changing rotations. So the benchmarking is focused on the factors that are more or less locked in. So the inherent soil properties and the general cropping systems, and the management is then that allows you to move the soil health up. Does that make sense? So the management is separate, right?
So maybe it's suitable for a local scale, not for a large scale range.
No, I mean,
scale region,
well, it's so we developed it for New York because we were asked by our state to develop it for New York. So, but the principles can be applied anywhere. You could. It's just that it's based on it requires a good database. It requires you to have, to be able to define the distribution of soil health outcomes. So it is very much data driven, right? And so there are areas maybe where the database is still insufficient.
Okay, thank you very much. Thank you.
All right, thanks again, Harold. I'll invite you to answer any questions that you see pop up in the chat. In the interest of time, we're going to go ahead and move along. I'm going to turn the program now over to Dr. Wang. And yeah, thanks again.
Okay, thank you. So our next speaker is Professor Yuji Jiang from the Institute of Soil Science, Chinese Academy of Sciences. He's an excellent young scholar of the National Natural Foundation of China. Today he will talk about community assembly and functional regulation of soil microorganisms and animals in farmland. So Yuji, the floor is yours.
Okay. Okay, I will. Oh, oops. Oops. Sorry.
Yes.
Okay. Can you see my?
Yes, I can see your slides, but you need to the play mode. Yeah.
Yes. Okay. Good morning and evening, everyone. I feel a great honor to be invited to attend this meeting. Today, I will talk about the assembly and the function regulation of the organisms community in healthy soils. First, I will introduce the backgrounds and the scientific questions. Healthy soil is likely home to about 59% of the species on Earth. It can store a great number of organisms, including the bacteria, fungi, protists, nematodes, earthworms, and other animals. These different groups of the soil organisms formed a complex food web. To gain a deeper understanding of the different ecosystems, we need to know how these organisms are distributed in healthy soils and what important roles they play in ecosystems functions. As we know, soil organisms are abundant, complex, and highly diverse, with millions of species often found in just 1 gram of soils. These soil organisms are involved in processes of the nutrient cycling, energy flow, and information transfer, which in turn affect the soil health and the plant growth. Basically, to fully understand what importance of the soil organisms played in the health of the soil, we need to know the community assembly of these soil organisms. The FOA proposed the December the 5th as a World Soil Day. To take stock the themes over the years, we can see that it is more or less related to soil health, especially in 2015. It emphasized that healthy soil, healthy life. Understanding the spatial distribution patterns of the soil organisms is a basis for revealing the soil biodiversity. As early as 2006, ecologists proposed to map the distribution of the soil organisms at the global scale. In recent years, with the development of the high-throughput sequencing technology, ecologists have completed the global distribution maps of the bacteria, fungi, protists, nematodes, and the earthworms. Therefore, understanding the spatial distribution patterns of the soil organisms is important to assess the formation of the diversity and its ecological functions. Like the terrestrial large plants and animals, soil organisms may also have the special distribution patterns, such as the distance decade relationships. However, there is no clear conclusion on how soil biodiversity is formed under the combined influence of the soil, pH, temperature, body size, and the predation. Therefore, the first question is that how does the diversity of the different soil organisms generate, and what is the dominant factors controlling it? Since the 1980s, ecological theory have held that the community assembly is completely controlled by the deterministic or stochastic processes. Recently, Valent has proposed a new framework for community assembly, which is influenced by both processes. This framework separates the two community assembly into 4 basic processes, including the selection, diversification, disposal, and the ecological drift. Soil pH and temperature have been found to be main factors influencing the bacterial assembly of the soil organisms. Besides, it should be noted that the body size of the organisms and the predation also affect the assembly process, which received little attention and largely limits the deeper understanding of the community assembly. The individual of the soil organism are small, but there are still orders of the magnitude difference in the body size. This difference can affect the generation times of their growth and change the community assembly of the soil organisms by its effects on metabolic rate, generation time, and the reproduction. Based on this background, we construct a model of the relationships between the body size and the community assembly. Selection is a fully deterministic process, where the ecological drift is a fully stochastic process, and the disposal and the diversification can be either stochastic or deterministic. Second, we hypothesize the relationship between the body size and the 4 processes. The smaller microorganisms can even survive in many extremely environments, and they may be less affected by the selection and have larger proportions that are more likely to mutate and the disposal. However, in populations of the large-sized organisms, the random survival and the death of the individuals may have less impact on a community. So in this case, the body size and the community assembly appear to have the positive, negative, or no relationship. So we ask the second question that, does the body size affect the community assembly of the soil organisms? The agricultural soils are reservoir of the biodiversity, and the soil organisms are important drivers of the nutrient cycling. The microfood web constructed by the soil animals and the microorganisms regulates the nutrient transformation and the supply. So cultivating the soil macroaggregates is one of the key goals in improving the soil fertility and the health. It will help us to build an efficient network between the soil animals and the microorganisms and strengthen the nutrient cycling. So we ask the third question, what is the principles of the functional regulation of the soil organisms? I will introduce the experiment and the designs and methods in the second part. First, at the continental scale, we sampled the paddy soils from the rice field across the East Asia, which include the 4 types of the crop rotations. The history of the rice cultivation was more than 30 years. Under this condition, we studied the special distribution patterns of the bacteria, fungal, and the proteus diversity in rice ecosystem. Second, we combined the rice ecosystem with other different ecosystems at a global scale to perform the meta-analysis. We collected a total of about 4,000 sample data sets covering the different ecosystems and extending the group of the organisms to include the nematodes. At the same time, we also collected more than 3,000 species and create a database of the birdie sites for the first time. In Yingtan Red Soil Ecological Experiment Station, we established the long-term field experiment of organic fertilization and multi-trophic introduction, and study the relationship between the community assembly and the ecological functions. We carried out the sequencing of the bacteria, fungi, and the protists of the communities, morphological identification of the nematodes, and the analysis of the carbon and phosphor metabolism. Next, I will introduce the results of our study, starting with the formation of the soil biodiversity. The soil pH is a main driver of the microbiodiversity in rice ecosystem. Bacteria and the fungi diversity increased with the increasing soil pH. And the soil pH largely affects the bacteria and the fungi community structure, with a strong controlling the bacterial community. To reveal the spatial distribution patterns of the soil microbiodiversity, the mechanism of the model bacterial diversity was further investigated under the different temperature and the pH conditions. The diversity of the individual and the community improved due to the increased mutation rates under the different environment conditions. So in this case, the temperature directly affects the metabolic activity, while the pH may affect the cell membrane, the protein activity, which in turn influence the mutation rate and the community diversity. Our study shows that the metabolic activity and the membrane, the protein activity was highest at the optimal temperature and the pH, which increased the mutation rate and accelerate the formation of the species diversity. At the national and the global scales, we innovate a couple of two-factor modeling with the temperature and the pH for predicting the soil bacterial diversity. Compared with the single factor models, its predicting the performance was improved by 50% to 110%, providing a new model for predicting the distribution of the soil animals and the microbiodiversity. We test a two-factor model in different ecosystems and the different types of the organisms. Overall, the two-factor model is more advantageous in predicting the performance of the soil biodiversity distribution than one-factor model. Meanwhile, the body size also affects the diversity of the organisms. In rice ecosystems, we found that a total of 26 dominant types of the three organisms groups with a relative abundance greater than 1%. Bacterial diversity is greatly higher than the protists and the fungi. For dominant species, bacteria has the highest average diversity, followed by the protists and the fungi. We then calculate the distance-decade relationship. The results show that all three organism groups have significant distance-decade relationships, indicating that all of their community beta diversity decreased with the increasing spatial difference. And the spatial distance is a more important driving factor for organism community and the dominant phylum compared to the environment factors. We also found the body size was negatively correlated with the diversity index and the slope of the distance-decade relationship. This result suggests that microbiodiversity decreased and the turnover rate of the community composition increased with increasing the body size. At the soil aggregate and the field scales, the number of the nematodes and the protists was positively correlated with microbial diversity. This suggests that the soil nematode and the protist predation may increase the microbial diversity. And the protists also shown the positive correlations with the diversity of the bacteria and the fungi communities at the national scale. We know that this correlation is stronger under the maize ecosystem compared to rice ecosystem. And then we further revealed the mechanism of the assembly process of the soil organisms community. First, we analyzed the assembly process of the bacterial community in red soil. Due to the high heterogeneity in the topsoil, the bacterial community was influenced by the strong selection, leading to the deterministic the process of the community assembly. Along with the soil depth, the community assembly changed from the deterministic to stochastic in deep soils. The acidobacteria and the chloroflexi were the two most dominant phylum in the bacterial community, and their assembly process was similar to that of the total bacteria. So these two dominant phylum may mediate the assembly process of the whole community. In rice ecosystems, we determine the body size of the 28 dominant groups, including the bacteria, fungi, and protists. Basically, the bacterial community has a wider niche breadth, large dispersal rate, and the smaller NDV views. These results indicate that the bacterial community is less affected by the environment selection, and the community assembly was controlled by a stochastic process due to the high dispersal rate. The dominant organism groups show the consistent patterns. And the body size was negatively correlated with the niche breadth and the dispersal rate, and positively correlated with NDV views. With the increase in the body size, the selection and the dispersal limitation increased, and the community assembly appeared to be a deterministic process. We then extend the body size of the organic organisms groups, including the bacteria, fungi, protists, and nematodes at the global scale. The results consistently shown the community assembly of the protists and the nematodes with a large body size tend to be deterministic. This pattern was well shown in different ecosystems. We also found a positive correlation between the body size and the NDV views across all taxonomic groups. It is shown that there is a general relationship between the body size and the community assembly, which is consistent with the rule we have found in the rice ecosystems. Based on the community assembly, we further study the function regulation of the soil organisms in the healthy soils. First, we found that the straw amendments increase the number of the nematodes and the bacteria, and in turn decrease the microbial metabolic equation and increase the CUE. The SEM analysis indicates that the nematode predation may increase the bacterial biomass and influence the community composition, thereby decreasing the microbial metabolic equation and promoting the carbon accumulation. At the aggregate level, the nematode predation also have a negative feedback on carbon metabolism. In details, bacterial nematode may feed on active bacteria and then reduce the metabolic equation and the carbon metabolism. This negative feedback is benefit for the SOC accumulation and promote the formation of the macro aggregates and improve the fertility and the health of the red soils. In micro aggregates, the SOC storage and turnover were mainly regulated by the microbial community structure, while in macro aggregates, the effect of the nematode predation increased and can change the microbial community structure to increase the active and the slow SOC storage and the turnover rate. So, and we also found the dual predation by the bacterial nematodes and the protists may further enhance the bacterial abundance and the diversity, and increase the carbon and the nitrogen metabolic activities in the macro aggregates. The effect of the nematode predation on carbon metabolism was verified by a soil microcosm experiment with a nematode addition. We found that the bacterial abundance, diversity, and the community stability were increased by the nematode addition. Overall, this positive effect was more pronounced in macro aggregates. With regard to the phosphorus metabolism, we focus on the bacterial channel under manure treatments. The bacterial, the nematode predation increased the abundance and the diversity of the ALP producing bacteria and the phosphatase activity. And this positive feedback can promote the phosphorus supply and increase the 8% phosphorus utilization efficiency in red soils. We construct a network between the nematodes and the ALP producing bacteria and revealed that the keystone species shared in the different the soil aggregates were all methyl rhizobium. We think that the predation by a dominant taxon of the bacterial nematodes has a positive effect on this keystone ALP producing bacteria. In microaggregates, the bacteria feeding nematode predation increased the phosphatase activity, mainly by affecting the abundance of the ALP producing bacteria. In large macroaggregates, the bacteria, the nematodes, change the abundance and the diversity of the ALP producing bacteria, resulting in greater promotion of the phosphatase activity. And this positive feedback will be better to active and release the phosphorus in the red soils. A soil microcosm experiment was conducted to demonstrate the positive feedback of the nematode predation on phosphorus recycling. We also found that the nematode addition indeed increased the ALP producing bacteria abundance, diversity, and the phosphatase activity in soil aggregates under the high manure treatments. We also conducted a long-term experiment of the biological introduction to verify the positive effects of the nematode predation on ALP producing bacteria and the phosphorus transformation in the field. Here we added the indigenous, the high efficiency bacteria, the nematode to the red soil. These 8 treatments can be divided into the non-nematode additions or nematode additions. With the nematode addition, the total number of the nematodes and the bacterial nematodes was increased, and then improved the 28% in the phosphatase activity. In non-nematode addition treatments, Brady rhizobium was the keystone ALP producing bacteria in the network, and the nematode predation enhance the phosphatase activity by increasing the abundance of the ARP-producing bacteria. However, nematode addition treatments increase the kind and the abundance of the keystone ARP-producing bacteria. These special bacteria create the strong competitive associations with other bacteria to increase the community diversity, and in turn to lead to 28% increase in the phosphatase activity. Take-home message: the soil pH, temperature, body size, and predation all influence the formation of the soil biodiversity. And the second, the body size regulates the assembly of the organisms communities. The third, the predation by the nematodes and the protists regulates the carbon and the phosphorus metabolisms by affecting the total bacteria and the ARP-producing bacteria community. Finally, we are grateful to Professor Bosun for his great support to establish the research platform, as well as to the collaborators for their help in this research work. Thank you for your attention.
Thank you. Very comprehensive presentation. A quick question: why is optimum temperature and pH will increase the mutation rate?
Yes, because if in the optimal temperature optimal pH, the metabolic rate will increase, so the mutation rate will increase, right? Yeah. So maybe if with a high mutation rate, there will form the more types of the species, so will increase the diversity. Yeah.
Okay, thank you. Thank you. And we have to move to the next speaker. So
okay, thank you.
Thank you. The next speaker is Professor Christine Wen from USDA Agriculture Research Service. She founded the Agricultural Society of America and also is president-elect. So, Christine, please.
All right, thank you. Yes, so it was the soil health community within the American Society of Agronomy that I founded. But today, thank you for the invitation, and I'm excited to share a new continental scale soil health assessment tool called SHAPE, and our future plans for expanding and improving SHAPE for landowners across the United States. So first and foremost, I want to recognize the SHAPE development team that has worked on this project for the past 6 years. So from the ARF, there's myself and Doug Harlan, who's now retired. From NRCS Soil Plant and Science Division, we have Sky Wills and Kathy Sable. We have Harold Van Ness and Joseph Van Seely from Cornell. Marcio Nunez, who's now at the University of Florida. And then our statistician, Scott Holen at the University of Missouri, and Paul Parker at the University of California, Santa Cruz. So the main objective with SHAPE was to develop a soil health assessment tool specifically for landowners that was based on laboratory soil tests. And it also has the goal of being low cost with fast and simple tests that can be provided by service labs. So that basically means nothing with a really large spatial or temporal footprint in a laboratory, or anything that's too high-tech or rapidly changing. For example, some of the genomics work that's very relevant to soil health, but might not be practical from a service lab perspective. And then we also don't have the ability to evaluate the macroorganisms, so we can't include anything like earthworms, unfortunately. And then for practical reasons, we focused on
the near surface soil, so the top 15 centimeters. And that way it can be compatible with what farmers typically do now for fertility testing. So, many decades of research have established the relative impact of management practices on soil health measurements. And so we've known for a long time, and generally speaking, that perennial systems have greater soil health, for example, than annual row cropping systems. And Harold talked quite a bit about this, and we've seen this data in the previous presentation. And we also know that soil health typically declines then within those annual cropping systems as we increase the soil disturbance or tillage and then reduce that crop diversity. But we also know that those inherent or site-specific conditions such as soil type and climate play a key role in constraining soil health values. And then across the United States, we have a wide range of soils and climate conditions. So if we're wanting to create a continental scale soil health assessment tool, we have to be able to account for these factors. And we know that these soil health values vary considerably across the United States, even under similar management practices. And so this slide just illustrates conceptually how pedology, or those basic soil forming factors, define your inherent soil conditions. And then through this lens of land use and management, we affect those dynamic soil health values, which are constrained by those inherent conditions. So the maximum values and minimum values will be constrained by those inherent soil characteristics. So then our goal with SHAPE is to account for those inherent conditions and allow for a site-specific soil health assessment. And we can provide landowners with a better understanding of how their management practices, or that fifth soil forming factor, how those decisions are impacting their soil. So SHAPE was formally initiated back in 2015 with an agreement between the Agricultural Research Service and the Natural Resources Conservation Service. But it was built upon decades of previous work and concepts that were laid out in the Soil Management Assessment Framework, otherwise known as SMAP, and the Comprehensive Assessment of Soil Health, so CASH, the Cornell system that Harold has described. And with these concepts in mind, we set out to improve the data set behind the scoring curves to better represent soils and systems across the US, and to improve those underlying statistical models. In many cases, and in particular with SMAP, the scoring curves were based on expert opinion instead of quantitative modeling. So it's no surprise we started out with soil organic carbon. Obviously, soil organic carbon is a keystone soil health indicator, but we also had a pretty substantial data set to work with. So we had over 15,000 observations that were compiled from Cornell's CASH data set, as well as data set that came from NRCS, from the Soil Survey Lab, and then data was compiled from the literature. So initially, we evaluated a pretty long list of potential climate and adaptive characteristics to include in SHAPE. And after extensive exploratory analysis, and given the size of the data set that we were working with, we narrowed the factors down to 2 climate variables, mean annual temperature and mean annual precipitation. And then we selected 2 soil variables, the soil suborder and textural class. But as we move forward and as our data set expands, we will revisit these factors and consider including more. And so what we do in SHAPE is we take these factors and we form soil peer groups. So we aggregated the data into 5 textural groups and 5 suborder groups in order to form, as I said, these soil peer groups. And then the climate variables are included as continuous variables in the model. So here's our basic statistical approach, and our first publication provides all of the gory statistical details if you want to pursue this in more depth. But just to give you a basic overview of how this works, the peer groups are defined by those 5 texture groups and soil suborder groups and adjusted for the climate variables, as I mentioned. But the curves are Bayesian model-based estimates of the conditional cumulative distribution function of CDF. So it's a distribution for a given soil peer group. And then what you get back are scores between 0 and 100% for your measured soil health indicator. In this case, we're talking about organic carbon. And that reflects the quantile or position within that conditional CDF. And it also provides measures of uncertainty. So you can think about this score as being similar to a percentile. If you have a child, you go to the doctor and you get height and weight measurements and you get a percentile. So this is similar to that. SHAPE also provides benchmarks, which currently it automatically provides benchmarks for the 90th, the 95th, and the 99th percentiles for that soil's peer group. And then the difference between the actual value and that 95th percentile, we consider that the soil health opportunity gap, or in this case, the soil carbon gap. So to give you an example of what these curves look like, as you move from left to right within a single row, the suborder changes. So you can see how changing the suborder affects these scoring curves. And then as we look from top to bottom within a column, the climate conditions change. So you can see the effect of changing climate on the scoring curves. The other thing to note about the scoring curves is that that green band is the uncertainty band. And typically, the wider that green band is, the fewer observations we've had in that particular soil peer group. So here's an example of a sample that had 2% carbon, and we entered that laboratory result along with the site characteristics into SHAPE. So we added the climate and adaptive characteristics. And this particular sample got back a score of 77% relative to its peer group. And on the right, you can see the peer group benchmarks that were returned for this sample. So the 90th, the 95th, and the 99th percentile. Because we're aiming high here, but you could also have SHAPE return any benchmark that you choose. So it could be, as Harold pointed out, maybe the 75th percentile would be your target. But if we use the 95th percentile as our benchmark value in this case, then we can calculate that soil carbon opportunity gap for the sample, which in this case is 1.6% carbon. And that's the difference then between the actual and potential soil carbon. In this example, we have 4 samples that are all at the same carbon content. So they're all 2% soil organic carbon. And here we're comparing the effect of climate, so in this case, Texas versus Iowa, and illustrating the role of soil texture. So in this case, comparing a sandy loam with a silt loam. So of the 4 sites, the Iowa silt loam has the greatest potential for organic carbon additions, and therefore it receives the lowest score, but it has the greatest opportunity gap. And in this example, we have 4 soil samples, all from the same site. So this happens to be our long-term agroecosystem research site here in Columbia, Missouri. But in this example, the site characteristics are all the same, but the soil carbon content varies as a result of the long-term management practices. And this shows that there are substantial opportunities to increase organic carbon in these systems. So after we worked on soil organic carbon, we moved on to some of the other soil health indicators, including 2 methods of aggregate stability, including the KSSL Kellogg Soil Survey laboratory method, which measures aggregate stability on the 1 to 2 millimeter fraction. Then the Cornell method, which uses the sprinkle infiltrometer. Active carbon, otherwise known as permanganate oxidizable organic carbon, 4-day soil respiration measurements, and then the autoclaved citrate extractable protein, or the ACE protein. And all of this data came from Cornell, with the exception of the KSSL aggregate stability data. So here's an example of what our current soil respiration curves look like. You can see, you'll notice, right away, those really wide uncertainty bands on that far column, and that is texture class 5. That's our high clay soils. And so we did not have very many observations in that peer group. ACE protein, similar curves. POC. And then here are the 2 aggregate stability methods. On the left, you'll see the KSSL curves have really wide uncertainty band. We only had about 1,200 data points to develop those curves. So for this first version of SHAPE, we have a Shiny app that's available to the public. Anyone can use it. And we also created a GitHub repository if you prefer that route. You can batch score samples. There are instructions on the website, but if anyone has trouble using that, you're more than welcome to reach out to me and I can walk you through it. And we also have our first publication in the Soil Science Society of America Journal, which describes in great detail the statistical approach as we applied it to soil organic carbon. And then our second manuscript is still under review, but that one covers the epoxy ACE protein, soil respiration, and aggregate stability curves. And then briefly, I'd like to introduce a new initiative, which is funded by, it was just recently funded by the NRCS. It's the Regional Soil Health Testing Project. And the goal here is to expand the data set from across the country to improve the SHAPE curves. So we recognize that we have gaps across the country in terms of soils and management systems. And we also want to expand the indicators that we offer and the methods that we cover. So for example, maybe a 24-hour respiration test in addition to a 4-day test. And then we also want to improve the underlying models. And we already have many exciting things in the pipeline there. But then as we expand the data sets, we'll be able to refine those peer groups, and perhaps instead of being lumpers, we can be splitters with our future scoring curves. So this new initiative to collect samples from across the US, the plan right now is to collect about 12,000 samples from a variety of soil health management, what they call SHMU, soil health management units. That's the level on which we'll be sampling. And it will cover cultivated, non-cultivated, pasture raised land, and CRP land. The sampling will occur starting hopefully this year through 2027. We'll tackle all 50 states plus the main US territories, the inhabited territories that are listed there. We'll collect management information. And phase 1 analyses will include organic carbon, active carbon, aggregate stability, texture, and pH. And then this part is still in the discussion, under discussion, but respiration, active carbon, some type of mineralizable nitrogen, ACE protein, and perhaps soil enzymes. And so our plan here, we have a spatially explicit version that's already in the works. I'm working on the first draft of that manuscript now. but we want better data coverage. So as many people have pointed out that spoke before me, your scoring curves are only as good as the data that you have available. So we need more data. And then once we have that, we can refine these peer groups to include broad land use categories, as Harold was describing, and be able to provide a more refined interpretation for landowners, and expand that indicator set and make it more user-friendly. So that's my introduction to SHAPE. Thank you for your time.
Thank you. This is very, very nice work. Any question? Okay, I see a lot. Wait. So the first one is the cache does not offer. I'm sorry. So the database support the SHAPE public available?
Well, so the new data set that I just described that will be funded by NRCS will be available through NASAS. So it's going to take a few years, but eventually that data will go into NASAS and it will be publicly available. Most of the data that's in SHAPE right now came from Cornell, so I'd have to let Harold answer for what his plans are for sharing that data in the future.
Okay, thank you. The next one is you currently cover crop had a benchmark score of 50. How do you use this score help provide management input to improve soil health?
So if I understand the question, it's how can this be used to improve management for soil health? Is that?
Yeah, because you have the score, and then how you apply the score, and later on could help the management to improve the soil health.
Okay, so right now your score is based on a peer group that's only defined by your soil and your climate, so your site characteristics. So at this point, you still have to infer something, and you have to know where the sample came from. You have to talk to the landowner. You have to understand what management practices are in place now. So if they score 77% and they're a row cropper, maybe an obvious switch would be to switch from row crop to pasture. But as Harold pointed out, people don't often want to do that. So as we build out SHAPE and as we bring in more detailed information that's associated with soil health measurements, we'll be able to refine that recommendation. So we'll be able to create peer groups essentially that are based on broad land use categories or even more refined management practices. So that will greatly increase the utility of the SHAPE system.
Another question is, can SHAPE be used in other countries, and is there a guidebook of how to use the SHAPE?
So you could use it. However, I think the ideal plan moving forward would be to create SHAPE for different countries or geographic regions using their data. So for example, the folks in Australia are interested in an Australian SHAPE. And so in that case, they have different measurements. They have, they have a completely different textural triangle. The categories are different. So there are unique factors that need to be accounted for in different areas, and maybe even different soil health measurements that you want to include. So yes, I think the SHAPE approach can be applied globally, but there may be slightly different factors or categories that we would want to include, and different soil health measurements, perhaps.
Yes, I think in the future this could be also used in other countries. And Harold mentioned you also have the apps for application as for the SHAPE. So in the future, if used for other countries, is this free for the farmers, for everyone, or?
Well, I mean, the goal is for that. I mean, the scoring tool will be free and available, and it's currently free and available. There's always going to be a cost associated with measuring soil health. And so here in the US, there are lots of programs that help cost share with farmers. But in terms of storing your soil health data, SHAPE is free. It's already out there. In fact, I think it's the Iowa Soybean Association has already taken SHAPE and included it on their platform for their farmers to use in Iowa. But the executable files are available. If someone wants those, I'm happy to share them.
And the last question is, can we make a soil health map, or is it already done? So this is maybe the question not only for US, and maybe for also for other countries.
Yeah, so as I just kind of glossed over at the end, our next version, version 2 of SHAPE, is a spatially explicit version. And so then we can make a soil health map from that. So that is in the plan. So we'll be doing that.
Okay, thank you very much, and thank all the 4 speakers for a very nice presentation. So finally, we have to move to the concluding remarks. So we would like to invite academician Professor Yongguan Zhu from Chinese Academy of Sciences to give us the concluding remarks. Professor
thank
Zhu,
you.
please.
Yes, thank you so much for this great opportunity. I think everybody will agree with me that we have just wonderful speakers from China and the United States, and all these presentations, I would say, quite complementary to each other. From the US side on the methodologies and the concept of assessing, particularly benchmarking soil health, and in the China side, a lot of data presented about soil biological properties related to soil health. I think that it is difficult to summarize all the key messages, but I can see that in going forward, I would say we need a more perhaps in-person discussion together in one room, have a round table discussion, because just having presentations, we didn't really have enough time to provoke new ideas, new methodologies, and new concepts in evaluating soil health, and how to aggregate the parameters into some numbers that can be used for the farmers and also for the policymakers. I feel that perhaps in the future we can discuss novel, fast, low-cost, and robust measurements or methods for large sampling in the field. That is one area we should think about. The other issue is about the big data. Obviously, we need as much data as possible. So in that sense, I think China and USA should really collaborate, maybe jointly have a big data set about these parameters, and to develop the benchmarking curve, and to understand the gaps for building up healthy soils in region-specific fashion. I think it is not possible to have a universal benchmarking, because the climate and the local environment, and also the land use scenario and the management tools are different. But we can perhaps develop some region-specific benchmarking for future research. The another issue I feel I myself has been focusing on soil microbial diversity research. We are still very much struggling how to really include bioindicators into the soil health evaluation, because the soil biodiversity data obviously it's a bit hard because there is a big redundancy in biodiversity. We all know that the biodiversity is important, but there is a huge redundancy in the soil microbiome and the soil animals. We perhaps needed to identify some of the keystone taxa, or even some of the rare taxa may play important role in terms of the community assembly and the key ecosystem services, for example, nutrient cycling, organic matter accumulation, and also carbon sequestration, attenuation of contaminants, particularly the agrochemicals, because in our both countries, we are using quite a lot of agrochemicals, and the residues will have negative impact on soil health. So how the microbial system will attenuate these agrochemicals obviously will be also important. I feel that USA is much advanced in developing the concept of soil health and developing the benchmarking. And China is in China side, lots of scientists are looking at the processes in different regions for soil health research. And I feel we can really come up some collaborative projects to leverage our efforts on the concept, on the methods, on the data, and also on the diversity of the production systems that we should consider for a more universal, I would say, soil health assessment. And eventually, we hope that our collaboration will bring also benefits to other countries, not just China and the USA. The practices in our two countries can be shared. For example, China is facing daunting challenges in safeguarding food security and also environmental quality. And on the other side, in USA, you have relatively more land in comparison to your population. So the global trading and the virtual movement of nutrients and the water is also something should be considered for global efforts in mitigating both food security and climate change. So my suggestion would be perhaps we can propose a workshop on soil health, and it should be held offline so that we have more interactions among the participants and a more intensive discussion. And maybe we should write up some joint publications regarding soil health, on the concepts, on the methodologies, and the applications for the real world. So, Dr. Zhang, I think that's probably what I can say at this stage. I must say that I'm thrilled by all the excellent presentations, and I have learned greatly from your talks. Thank you so much, and I'll pass on to Wei for you to chair the last minute.
Thank you so much. We are right on time, and so I think just a couple remaining comments from the Q&A section. So the future roundtable, in-person roundtable workshop is a great idea, and I also encourage the panelists to look over the questions on the Q&A and to answer those. And with that, is anything else that needs to be discussed or brought up at this point? If not, we really appreciate everyone's commitment and efforts to make this webinar successful. I think there's a great discussions. So future webinar gonna be planned next year. So stay tuned with the announcement from the Soil Science Society of America and the Soil Science Society of China. Thank you. I would propose that we adjourn this webinar.
Thank you. See you next time.
you.
We must meet.
Thank you.
We must meet in 3
Thank
dimensions.
you.
See you
Thank
next
you so
time.
much.
Bye,
And
everybody.
especially for
Bye-bye.
James.
Bye.
Thank you.
Thank you.
Thank you. Bye-bye.
Bye.
Bye-bye.
Bye bye.